everyone. Good morning if you're in France. This is morning still. Good afternoon, good evening, or good very early morning, depending on where you are today. I'm very happy to introduce our first speaker for today at the Mathematical Summer in Paris, Jacques-Olivier Moussafir from Morgan Stanley. He will talk to us about ideas from mathematical finance. I would like to remind everyone that if you have questions during the talk, you can type them in. We will see them and we will ask them to the speaker after the lecture. Jacques-Olivier, please, the floor is yours.
Thank you very much. So welcome everyone. So I'm going to try to give you some overview of the very numerous developments of mathematical finance. So as we speak, it's a very, very wide topic. It's something that's covered by many universities, whether in France or everywhere in the world, and it has become something really, really large. I would like to start with say what I think is its starting point. If you think about, say, the mathematical developments from the 19th century, it's rather clear that everything stems from calculus. So derivatives, integrals, then multivariate calculus, and then all equations from physics. and to some extent, obviously led to huge successes, etc. And it's very clear that, by contrast, the situation is relatively similar with mathematical finance, but the starting point is not only calculus, but probably most very clearly it's probability theories. So I'd just like to just frame the various steps that related to the development of probabilities in general. So you obviously know that Kolmogorov in '33 did actually sort of laid the foundations of probability as we that we use today. In his foundation is really something which is relatively technical. So I don't know if you're aware of that, or how complicated it can be, or how technical it can be. But first, so just to give a couple of dates. So mid 19th century, we have Robert Brown's observation where he was looking at small particles of pollen in water and was observing some random motion or some very wild motions, sort of. And it was probably the first real-world observation of what is going to, what we call nowadays Brownian motion. So one very important step in the development of mathematical finance and usage of probability is the PhD thesis of Louis Bachelier. You can actually read the PhD online. It's available. It's relatively interesting because it's not so technical compared to modern textbooks, and you have tons of ideas in there. Unfortunately, I would say there is in the middle Lebesgue integral. So we need this absolutely because Lebesgue integral is about measuring surfaces and volumes, and probability boils down to measuring relative volumes in some spaces. So it becomes the very key technical component of all the probability developments that came afterwards. It's also worth mentioning that the contribution of Albert Einstein in the understanding of Brownian motion is also one key step. Norbert Wiener, I just want to mention the name, but I won't describe what he did. So Andrei Kolmogorov is I think, credited for the axiomatic description of the probability theory. And in his description, essentially, it takes Lebesgue integral and phrases it or adapts it to the context of probability. One very important person in this context is Paul Lévy. So he worked on what? Oops, there's a typo. So he worked on something which is called martingale and Brownian motion, which I'll be talking in a minute. And from there it became so it was sort of after that there was some sort of explosion, like taking all this apparatus, all these technical elements, and trying to build models, understand, ask questions, phrase questions, etc., etc. On a more recent, so more recent developments correspond to something which is called mean variance analysis. I won't talk too much about that. This is essentially something which is related to building portfolios. So I'll leave that aside in this presentation. One thing which I'm going to talk about is something which is called CAPM or factor model. This is from 62 and 64. So you'll see at the end of the presentation how it looks like. Then the big thing, maybe you heard the name of Black-Scholes. So this is something I'm going to dig into. This is recent, but not so recent. And something which is really very recent is something which is called econophysics. I won't have the time to talk about that, but just to mention briefly. So in the economy in general and in finance in general, you have interactions between many individuals, companies, players, if you wish. And these individuals or players are so they are seen as sort of small particular agents, and from their interaction, because there are many of them, you see some macroscopic things emerge. And so you have some sort of analogy between what you have in statistical physics and what you have in finance. So this is a huge chapter. You now have journals, books, etc. on that topic. I need to just to present very briefly what we call random variables and and the basic settings of probability. I'm going to try to be non-technical. So I'm going to say the minimum. There won't be much things. I think it should be all fine for everyone, but just keep in mind that the full theory is very technical. So the simplest example that you know of probably is the heads and tails game. So when you play heads and tails, you have a coin, you throw it in the air, it falls back either head and tail, and you have this idea of you have one chance out of two of the coin being on heads or tails. And so usually we say that we have some function which has values in -1, 1, and we have the probability of x being 1 to be 0.5 and probability of x being -1 to be 0.5 as well. And this is obviously if the tail is fair. So if the coin is fair, sorry. The next simple example is the case where you have some random variable whose values are either in a finite set, say 1 to n or z, so just the integers. And in that case, instead of having two numbers to describe the probability, you have either n numbers or an infinite set of numbers. And the only condition that you need to ensure is that all these coefficients are positive and their sum is 1. So that's the usual say, not so technical framing for probability. And finally, random variables can be real valued. And if that's the case, instead of saying that we know the probability that x is -1 or 1, we express that we know something about that random variable, saying that we know the probability that x belongs to a segment AB, and this is equal to the value of some integral of a function, and that function is positive, and its integral over the real line is 1. So normal distribution is probably something you've heard about. So it's something that we see everywhere. Distribution of a quantity which can be positive or negative. It's usually very frequent that you come across something like this. And so the blue dot on the horizontal line is just a random sample of this normal distribution. And I can repeat the experiment of drawing a number from the normal distribution. So it's important to note from the building of intuition that if you want to play with a random variable, your computer is your best friend in a sense, because if you use Python, for instance, you have loads of distribution already implemented in Python, and so you can just play with it and just throw random numbers, and it will give you a sense of how random variables can behave, and then you can start to play a bit with everything. Obviously, if you draw hundreds of values of that normal distribution, you can plot an histogram, and that's what I just did here. And then you have vertical bars that describe how frequently you got values around 0, how frequently you got values around 1, -1, etc., etc. So this is probably something you're familiar with, but it's just a reminder. A very key concept in probability is the idea that two random variables are independent. Being independent means that very informally, you don't have any relationship between your x and your y. And so if you have some random x, a random value of x and random value of y, you cannot make any guess on y if you know x, and conversely. If you want to be slightly formal and do some computation around this, it's for random variables whose values are finite or discrete. It's expressed in the following way, and the probability of x is A and y is B is just the product of both probabilities. And as a sort of not counterexample, but an example of things that are not independent, if I take two random variables independent, and then I build x to be A and y to be A plus B, they are not independent. And that's and you can figure out this directly from calculation, but the intuition should be relatively clear. If you fancy pictures, you can take two independent normal variables, x and y, and draw a sample of x. So say 100 values, and again 100 values for y. And if they are independent and you plot the coordinates that you got from your sample of x's and y's, then you'll get what's on the left of the picture. But if instead you do what I described with A and B and x and y on previous slide, then you'll get a picture which is going to resemble what you have on the right-hand side. And so obviously you can say something on y if you know the value of x. So I'd like to spend just a bit of time to show you how the Brownian motion was built from the things I just presented. So the Brownian motion, it's the idea of either a particle moving, say, randomly in 3D space or 2D space, but we can obviously do Brownian motion in one dimension, and this is how it works. So before, the first thing I need to build is not the Brownian motion itself, but a random walk. So a random walk is, say you are on a straight line, so you are the blue dot on my vertical dotted line, and you are going to make one step on the left or one step on the right, based on some normal random value. So the red curve that you see shows the distribution of probability for your first step. And so if you just throw a random number based on that distribution, then you may end up at the second blue point, which I just spotted. And then you can repeat this experiment. So you can take another step and now take a second random number with a normal distribution. And then again, I had in red the density of my normal distribution. And you see that it's precisely centered at the value of my first point. So I have another point like this. And then I can repeat a couple of times this procedure. And so each time I have a step on the left or on the right, just based on my new number, which is drawn from a normal distribution with mean 0 and actually standard dev 1. And so I repeat and I go up or down. And then, as you can see, I have some, I have some random path. And in that specific case, it's not a continuous line, it's a discrete process. So I have a discrete set of values. And from the equation perspective, everything is written like this. So the first value is 0. The value x1 is just a normal distribution, so with mean 0 and standard deviation 1. So that's the bell curve I plotted in the very beginning. Then the value for x2 is the previous value plus random variable, normally distributed and independent of x1. And for x3, it's exactly the same. It's previous value plus a normal random variable independent from x1 and x2, etc., etc. And so you can get a sort of a path like this. And that's the first step when in the construction of the Brownian motion. What you can do with that construction, you can make smaller steps. So instead of moving to the right direction by 1 each time I get a new number, here I'm going to take a random number which is normally distributed. The mean is going to be 0, but the standard deviation is going to be 1 divided by square root of 2. And so you see, I'm just refining the procedure. And doing so, I get a path which is still discrete. So I still have a discrete set of values, but it starts to look like something continuous. And you can imagine that I can just refine again and again. And if I do so infinitely many times, I end up with what people call Brownian motion. So in a sense, the Brownian motion is just random walk, normal steps, but infinitely many of them. And from the formal definition of the Brownian motion, it's a bit, it's relatively straightforward from what I just described. And you have, for instance, relatively complicated theorems about the very existence of the Brownian motion, because if you've been doing some integration, having, or even Lebesgue theory, having some measure on some product space is something which is very technical. The only thing that you need to know from the computation perspective is that WT is normal, so it's normal. It has mean 0 and a variance t, so it's distributed like normal mean 0t. And the increment, so wt minus plus h minus wt, is distributed like a normal distribution, mean 0 and variance h. I'd like to make now one remark about the Broad motion. So that's in the Louis Bachelier PhD report. I'm not sure from when people made the remark for the first time, but what I noticed is that there is something which is there is some analogy with physics, and it works like this. So if you take one metallic bar, so which is infinitely long, straight, it's homogeneous, and most importantly, it's insulated. So you have around that bar, you have say something that makes the heat contained within the bar. If you hit the bar in its center for say 1 minute, what is going to happen is that you'll have a very high temperature at x equals 0, and then gradually, if you stop heating, the temperature is going to become increasingly uniform across the bar. And so if you observe this, you'll get probably something which will look like that. So this is so let's say that so this is the x-axis on my metallic bar, so that's the position along the bar, and this is say the temperature. So the unit is probably not very relevant, and that's the temperature say at time maybe 0. After some time you'll have something like this, and after a longer period of time you'll have something like that. Oops. And so what is striking and what is the core of the analogy between heat equation and probability is related to this thing. WT has a distribution with mean 0 and variance t. So as so the larger the t, the wider the distribution. So it's like a bit. It's a bit like if the Random-Walk distribution was exactly sort of the temperature of the metallic bar. So we have something like this. So the temperature at time t point x is the exponential of minus x2 divided by t square. And so that's the analogy. And at that stage, it's just an analogy, and there is no reason to think that that the temperature is actually behaving like the density of WT. That's the heat equation. Actually, so this differential equation, it reads, so the reading of it is very, very, I think, intuitive. So it says that if you have a function, so that depends on time and position, the rate of change of the function with respect to time is proportional to the curvature, which means if we go back to this graph, so if you take that point, so you see that the curvature here is very negative. So at next time, the value of the function at that point should be lower. By contrast, if you take that point, then here you have a positive curvature, so it should move up. So heat equation is really something like, it's a bit like a smoothing. So you need to, I think it's important to read this equation like change in time is proportional to curvature. So this analogy is not, is actually these days very well understood. So it's like a very significant fraction of mathematical finance is actually study of PDE, like heat equation. There is also a famous one whose name is Fokker-Planck equation. So it's about the evolution of density distributions. Another one, which is Feynman-Kac equation, which is heat equation with time reversed. So all this is very, very normal, and we understand very clearly why why we have such a connection between physics and probability theory. Just to give you a tiny sense of how it looks like in, say, real life. So this is the US stock market between 2015 and 2018. I think it's like something like all the stocks corresponding to one big US index, which is the S&P 500. And so, as you can see, it's juggling up and down. As you can see as well, you have big jumps like this and like that. So, for instance, there are still tons of debate about whether the Roland motion is the right model for financial stocks, and I will be discussing a bit this question later. First problem maybe that you can think about if you want to it's relatively easy if you want to get used with these random walk questions and how they work and etc. So assume that you have xn, a sequence of random variables. Initial value is 0 and xn is previous value xn minus 1 plus un, and un is sort of a head and tail, but it's not fair. So it's not 0.5 probability. It can be p1 minus p. And so the question for you is, what's the distribution of xn? So that's an amusing exercise. And I think that if you go through this, then you'll see a first connection, not with physics here, but with combinatorics, because you'll see something which is going to resemble a lot to binomial coefficients. So next question, if you wish, you can elaborate and try to figure out what's the relationship between the distribution of xn and distribution of xn minus 1. And in this context, you may wish to write a discrete form of the heat equation. So that's an amusing exercise. And maybe you'll get the sense that really binomial coefficients, Gaussian distribution, and heat equation are related. One relatively amusing exercise also is about this process xn. And one relatively easy question is to figure out the probability that xn gets larger than, say, some number a at some time. And the next question is, what is the probability that xn goes above a at some time and then goes back to 0 at a later time? So it's if you think about this as a game and you win +€1 or lose €1 at each time, so it's the probability of getting richer than a at some time and losing everything at the later time. So if you figure out the answer, you'll probably get depressed, but that's life. So one very big chapter in the context of mathematical finance is arbitrage and pricing. So just to recap very briefly, so we have probability theory, random variables, etc. We have built on the top of probability discrete time random processes, so cumulative sum of +1 - 1 probability p1 minus p. We have the Brownian motion, which is the continuous time version of the random walk. And now there is a big question, which is very similar to the kind of questions that you get in insurance. So, so let's start with something. So what I'm going to describe now is something which is called the Cox-Ross-Rubinstein model. It was proposed, I think, at the end of the 70s. And it's very, very close to what we call the Black and Scholes model these days. And it sets the landscape for what we now call pricing. So assume you have something, so it can be anything, so French baguette if you wish. And let's S0, S1, ST denote the consecutive prices of that thing. So and assume that the prices behave that way. So first of all, the initial value S0 is positive. Then the value at time t is u times the value at st minus 1. So and it's d times the value of sorry. This is with probability pu, and with probability pd, which is 1 minus pu, the value of st is d times the previous value, and obviously, and d equals 1 divided by u. So this is more or less exactly like the random walk we discussed before, but we're just taking the exponential of it. So it's like instead of having +1 minus 1, say you multiply by 2 or you divide by 2 at each step. So it's just exponential of the random walk. And now imagine that that you have some, so you have a lottery, and the lottery works like this. So you are at t equals 1, and if you buy a ticket at time t, you are going to be paid by some function of the last value. So f of st, and so f is any function, so it can be so anything, and so and one key point there is that the lottery takes place repeatedly, so it's like every week or every month, so you can play it again and again. So this is something which is going to justify some argument in what I'm going to explain. And so key question, and so that's the very common question in mathematical finance, is what's the price of the lottery ticket? So how much would you be willing to pay now, so at t equal 1, to get a ticket for that lottery with the potential outcome of f of st? So that's a tricky question. It's not that simple, and I'm going to break that problem into hopefully understandable and smaller pieces. So let's assume that so we are at t equals 1, and so in my example, the outcome of the lottery is going to be known at t equals 2. And so we have the situation of at t equals 2, the price of st is going to be either u times s0 or d times s0, this with probability pu and this with probability pd. And the question is, how much are you willing to pay now to get a lottery ticket that will give you these values? And what I call a sensible answer is actually has says sort of a very clear justification. So the sensible answer is the expected value of f of s1. So it's just this. Why is it so? So that's reasoning which is outside of mathematics. The reasoning it works like this. If the price of a ticket was larger than this, essentially no one would buy it because you would pay something that would, on average, give you back something less. If instead the price was strictly below that value, everyone would get it because on average you would get a larger value. So that's so the idea that the price of the lottery ticket is this value is not a mathematical consequence of the modeling. It's just based on something we call an arbitrage reasoning. And if you want to make things theoretical, then you need to jump into game theory, which I don't want to do now. But so this expected value is really the value below which you have some free lunch, if you wish, and if it's above, no one is going to buy it. So it must be it. and so this is my arbitrage argument. And so we have this picture. So you compute the value of the lottery ticket at t equal 1 from the value of what would be the, sorry, from the value of, so to speak, the lottery ticket at t equals 2. Now, let's assume that we are in a slightly more complicated situation. You have the initial value of your thing, so it's S0 times equals 0, it's U S0 or D S0 times at times 1, at time 1, sorry, and it's U square S0, UD S0 or D square S0 at time 2. So again, you have this lottery question. So you'll get this at time 2. How much would you be willing to pay at time 0 to get that? And so the reasoning works exactly in the same way. First of all, so again, expected. So the answer is the expected value of f of S2, which writes exactly like this. So trust me just for a minute on this. And then what we do here is something which is relatively similar to dynamic programming. So I don't know if it's something you're familiar with. It's the idea that if you know something in the end, you can sort of move backwards. And my argument is a bit like this. If you think there is some intermediate lottery and that you're allowed to buy a ticket at times t equals 1 instead of 0, you could get its prices from the previous lottery where we had just one time forward. So and so in a sense, we are going to derive the price of this new lottery at time 1, and from these prices, we are going to get the prices at times equals 0. And so if you want to see everything on the picture, which is the way I prefer to present this kind of computation, so you get that value and that value, and from these two values, you can get the price of a lottery ticket at that time. So at that time, if you know that the price had just moved up, you would be willing to pay that value to get either f of u square as 0 or f of ud as 0. And instead, and if the price had moved down on the first step and you were here, so this would be the expected value of the lottery condition to the fact that you have moved down on the first step. And then you can take these two values and apply exactly the same reasoning and get your initial value. And so that's how the price are computed. So it's always based on arbitrage, it's always moving backwards, and it's always, in a sense, computing the average values of what's on the right. So if you think about, I don't know if you're familiar with Euler project, you have dozens of problems where you have some terminal thing and then you want to compute the things at the initial value. It works exactly in the same way. Now I need to sort of generalize a bit further and sort of simplify also a bit. Assume that the function I'm using is a bit peculiar. So now I have 6 steps. So and you'll get something if the value at time 6 is precisely S0. And then question, what would be the price? And then it goes like that. what you can see on this diagram is essentially exactly the diagrams that we had before. So it's like up or down, probability of going up is PU, probability of going down is PD. I didn't draw the straight lines that connect all these dots. The only thing that you know is that at times equals 6, what you will get is this value if the price is precisely as 0, and 0 if it's above, 0 if it's below. And then the question is, what should be the price at this time? And we can apply here exactly what we just described, so move backwards. So the price, say here, is going to be the average based on the probability PU and PD of this value and this value. And the price here, for instance, is going to be the average, again, based on PU and PD of this value and this value. So you can move one step backward and you get this shape. And again, this red curve corresponds to the value of a ticket at times equals 5. So if you were, so if we are at t equals 5, but in one of these states, and you want to know the price of the lottery ticket based on this value of the ticket at times equals 6, then you have this thing. And you can move again one step backwards, and one step backward, and one step backward, and again, and again, and then you get the price. And so this is the price at the initial value. In terms of equations, it's just a piling up of averages. And so, and again, probably it must ring some bell about combinatorics and binomial coefficients. Then there is one question that comes next, which is if you say that that you get something if the price at time 6 is 0, then so you get that tree. But say the price, you want to know the price of the lottery ticket as a function of the initial price. So this is a bit, so you are going to get €1 if the price at time 6 is S0, and you want to know how that price depends on the initial price, and the initial price being either S0 or U times S0 or D times S0. And then, so that's a new setting, and so you want to have the price of the ticket as a function of the initial price. And so here everything applies, so there is no changes. So it's really completely straightforward. You simply need to make a copy of the big triangle I had on previous pictures. So instead of having one triangle whose top is here and who goes say like this, I take a copy of that triangle, I shift it up by 2, shift it down by 2 here, so 2 is not relevant. And then I'm going to apply my backward process, and it's going to work exactly like this. So essentially what I'm doing is, instead of propagating backward my red curve on the grid I had on the previous pictures, I'm going to propagate backward my grid on some extended grid. So oops. And so this is how it works. It goes like this, and then you get the prices at initial time for your lottery ticket whose value is etc. etc. So so that's the next step, and then the final step I want to dig in this Cox-Ross-Rubinstein model is actually the real world case because the lottery ticket that most people deal with are based on the following rules. So at time capital T, you are going to get ST minus K if ST is larger than K, and else you'll get 0. And so this is something that people call a call, so it's a call option. And so capital T is called the maturity, K is called the strike, and to get the price of this on the setting I just described, we are going to proceed exactly in the same way. What you can see on the right-hand side is this value of ST minus K. So in my example, K is 0. So you can see that here the value so here the value of the final payout is going to be 0. If ST equals, so is at that level, then the value is going to be this positive number here, and it's going to grow linearly, so straight line, so an increasing. So the further up ST, the better in terms of lottery ticket, and if ST at final time is below K, then you get 0. And then you go, oops, you compute your averages. So just to repeat once again, so the value that we have here, so this small red dot here, is just the average of this value and 0 with the coefficients P, U, and PD. So I can move forward, so it gets smoother and smoother and smoother and smoother and smoother, and you get eventually the value of your call option at initial time, and that's essentially how people do compute the price of call options. But I left one key question. So you remember that in my model, I said that the price of so the sequence of prices S0, S1, etc. up to ST are moving up or down based on probability PU and PD. But what I didn't say, if you want to consider so the real case situation where you have something whose price is going to change according to these rules, I don't say anything about the value of U, the value of D, and I don't say anything about these probabilities. So assume that you have, the object you're considering, say, is a French baguette, and so its price is going to move up and down, and then you have a lottery ticket to about this French baguette, and depending on its price, after say 20 period of time, you'll get something if the price is above say €2, and you get nothing if it's below. How do you set these values? So this is a key question. One thing which is very, very amusing is that all the PDE and technical tools to solve what I just described before. So all this was known, I think, in the 50s, and it took something like 30 years to figure out what should be PU and PD, what should be U and D. And the answer is the following, and it's very, this is not easy. This is something that I would say most people miss, and which is not very intuitive, etc. For the value of PU and PD, it's again some arbitrage reasoning. So it is essentially saying that the price of a baguette, on average, should increase like inflation, no more, no less. So if that's the case, we can figure out what is the expected value of S1, and the expected value of S1 should be this. So R is the rate of inflation, if you wish, And from the value of R here, you are going to be able to derive the value of PU and PD. So the ID, and so this is the fundamental economical ID, and this is the fundamental, say, cornerstone of mathematical finance. The probabilities of moving up and down are essentially based on inflation. You cannot make any sensible guess about the evolution of the price of baguette apart from the fact that it's going to follow inflation. And for the values of U and D, essentially, it's going to be related to what we call volatility, so which is the magnitude of move of the price between two dates. So in this setting, so in the model and in the parameters that we inject in the model, it's very important to, so in this area, it's very important to notice that on one hand, we have parameters that correspond to, say, arbitrage reasoning, so like PU and PD. It must produce something which is the inflation, and we have parameters that correspond to what has been observed in the past, which is the magnitude of change of prices of the French baguette. So understanding that you had something that comes from observation of the past on one hand, and taking something which is based on arbitrage and relating the price of things to inflation is something which actually produced the Black and Scholes formula and all these pricing models. And so it was, I think, at the end of the 70s. And then you can go from the purely mathematical setting to the real world application where you have actual lottery tickets related to actual objects. So that's the end for the pricing. And the thing I'd like to present now is something, so it's another big chapter of mathematical finance. It's totally different. It's a bit in the middle between economy and finance, and it goes like this. In mathematical finance, so when you look at the economy in general, if you look at the automotive industry, financial industry, or pharmaceutical industry, so there is this general sort of agreement or belief that there is something that drives them. Or maybe if you take all the companies in France, obviously they are different. Some behave well, and so some other do not. But in general, they are sort of driven by the fact that they all belong to the French economy. And you may want to say that if the French economy is doing well, it's relatively likely that on average, each company in France is going to do well as well. And so it goes to some sort of, it leads to some sort of model like this. So it's the idea that there is something which I call empty. So think about, people call that the market. So it's like the underlying unobserved thing, which is going to drive the French economy. And each price of stock on the French market is going to behave like the market plus something. And so this is a random walk exactly similar to the one I described on the first slides at the beginning of the presentation. This is also a random walk, so like a normal random walk, so mean zero and standard deviation, whatever. And if you look at that, you just have this idea that you have something that drives everything which is unobserved, and something which is observed, and which is the unobserved quantity plus something. So this is the simplest example of factor model. I'll come, so for instance, I just, here I've just plotted a couple of trajectories. So each trajectory on this graph corresponds to one of my XTI. So it's moving up and down. And in this example, I built myself, so something which is empty, which is not known to the observers, but I know where it is. And so it is precisely there. So, so my model is just it's like this. And if you look at, say, the prices of the French of the stocks of the French companies, it's more or less like this. So it's like a bit everything moves a bit in the same direction, but not exactly in the same direction. So, for instance, you can see that this blue one at the top, it's doing something, but it's not exactly the market. So, so that's the general picture we have in mind. And then we have the big question. If you observe all the blue lines, how would you be able to recover the red one? And so that's the estimation of the unobserved thing. That's something which is that's a very classical question. It's something which has been debated in various contexts, like position detection of something. So the keyword here is Kalman filter, and that's certainly a very difficult question. But an even more basic question is how would you prove that there is some hidden factor? And so I leave it to you as a not as an exercise, but because there is no definite answer to that question, but just about how would you do it yourself? How would you phrase the problem? How would you say, look at the blue time series and try to figure out if there's something hidden? So this is one of the keywords is Kalman filter. One other keyword is hidden Markov model. And hidden Markov model. So I don't want to explain what are hidden Markov models, but it's like you have something hidden, and on the top of this thing which is hidden, you have something added, which is random, and you try to infer what's hidden from what you observe. So in this context, there's one very, very important algorithm which I'd like to explain. I think it sheds some light on the kind of subtleties and tricks and amusing ideas that you have in this context. So there is an algorithm whose name is expectation maximization. So it's EM so for short. It's actually not an algorithm. It's more like a heuristic. So it's going to find some local minimum. And instead of dealing with my factor model, I'd like to take one very, say, plain example, which is in nature relatively similar. So assuming that you're teaching, so you're a professor, you have you're teaching, say, mathematics, you are going to set an exam for your students. And then you, and so there are many of them, and because you're slightly sadistic, then the grades can range from -infinity to +infinity. And so it's so you have 1,000 students, and the grades obviously are the higher the better. And assume that you have this histogram. So so you have a collection of notes, say around 25, a big collection around 5, and from the picture you really get the impression that you have two groups. You have a group of not so good students and a group of good ones. And because you're very conscientious, you'd like to figure out how many of your students belong to the first group and how many belong to the second group. And you'd like also to get an estimate of the average grade of the good ones and the average grades of the not so good ones. And top of it, the standard deviation for the notes in each group. So it's so that's a problem that I think every one of us either faced or will face someday. And there is a very neat answer to that question. And it goes like this. So first of all, I'm going to give a naive version of this algorithm. But say you start with random estimates for the average note for each group, and with random standard deviation as well, and you just have random estimates for the probability of belonging to the first group or the second group. One thing that you can do relatively easily, you can decide if one student, so you can figure out or compute the probability that one given student belongs to the first group, and similarly the probability that one given student belongs to the second group. And so if you make the assumption that the grades for the first group are distributed like a normal distribution with mean mu0 and standard dev sigma 0, and if similarly you make the assumption that the grades for the second one are distributed normal mu1 and standard deviation sigma 1, you can, for each grade, you can compute the value of the density of the first density for your grade, for the grade you chose, you picked, and the density of the second distribution for the same grade. And you can compare the two, and then you are going to decide, okay, this density is larger than this one for that specific grade, so maybe the grade that you picked belongs to the first group. So this is also part of the main, sorry, I forgot to mention this. So this is a problem. And once you've assigned each student to a given group, you can compute the mean of their grades. So based on which group they belong to. So say you had the 1,000 students, you did split, say, into 800 and 200, based on the values of the density of the normal distribution on each grade. And then once you've done that, you have two groups, and you can compute the average for the first group, you compute the average for the second group, and then you have a new estimate for mu0 and for mu1. You can also compute the standard deviation within the first group and the standard deviation within the second group. And based on that, you'll get new estimates for the average grade for the first group, and also an estimate for the average grade for the second group. So you'll have that split, and you can iterate. And that's what I'm going to show you in a couple of graphs. So in this context, this is exactly what I did. So I started with random estimates. I compute the value of the density of the normal distribution with my two initial guesses for each grade. Based on these densities, I decided to split the grades in two groups, recompute the average grade from one and for each group, recompute the standard deviation, and start again. And so, as you can see, in a couple of iterations, so in my example, I just have 15 iterations, I get to the point where I do have very precise estimates of everything. So having done that, I can compute the probability that one student becomes to one group. And the funny thing is that this was not observed. So if you remember about my factor models, I was trying to figure out something which was hidden and I didn't have access to. And in this case, I have a very, very similar situation. There is something which is hidden, which is which group each student belongs to. I only observe the grades, but from the observation of the grades, I can go down and infer each group for each student with some probability. So it's not a clear cut, but it's definitely something which which makes it possible to make some interesting guesses. So this algorithm is actually one. It's in the family of clustering algorithm. It's called EM, and it's something which is playing a very, very, very important role in the context of hidden Markov models. So that's going to. So let me recap just on this slide what I just described. Oops, I think. Oops. So I get initial guesses for the average grades in each group. So just random, purely random, and for the proportions. Then I find from so I compute the density of my first distribution for each grade, and I compare it to the density with mu2 sigma 2, and I count the number of grades where the density where the first density is larger than the second. Same thing for the second distribution. So there is a typo. I update my guesses, and then I go back to my second step and I iterate again and again. So this is a naive version. And so one of the problem that you may want to think about is how to improve that naive version. So by the way, I didn't mention something to Pierre, but I have a couple of notebooks with all the code and all the examples coded. So if you wish, I can just send this through. And then there is a big question, and again, it's very, very open, and you can really try to make your views on it. But it is a fact that EM can be used to estimate the market in my hidden in my factor model. So I'd like to recap again on these two modelings. So Brownian motion, which I described in the beginning. So it's something which is going to be used for finding the prices of things with these slightly complicated arbitrage reasonings in the middle. First, to understand how the backward propagation of prices works, and second, how to figure out the various parameters in the model. So that's one thing. And the factor models are more like trying to understand the underlying dynamics of all the prices that we observe and try to figure out the factors. And so I'm trying to use that to provide, say, fair prices. So because say, let's say that the French market, so I'm not totally France focused, but just as an example. So if you take the French market, say it's plus 1%, minus 1% every day in terms of change of values. Then if for some reason you don't observe the price of one stock, say BNP, then you may guess the value of BNP based using that sort of factor model. So a factor model is something that will help you to define the prices of things that you don't observe, for instance. But there are many other usages, but that's one possibility. One thing which is important and you can play around for quite a while is that the two models are presented above. So Brownian motion on one hand, the factor model on the other hand, have tons of variations, so they are monovariate. They can be multivariate. If you fancy continuous time, it can be continuous time. One example that I'd like to briefly mention is what we call stochastic volatility models. So I'm starting from the Brownian motion, and or more precisely, let's say I start from the random walk. So I have the initial value, I have the increment are just like this, and then question what happens if this parameter sigma, instead of being a parameter, is itself some random process. So, and in terms of modeling, maybe just forget the equations for a minute. So, so sigma is going to be random, and the reason why I would like to make sigma random is based on the fact that we observe in the market something which is very similar. So when we look at, say, the change of prices in various things like say this BNP stock or Renault or whatever. So if the market is relatively quiet, the price is going to change by say +1%, -1%. But if you're just in the middle of the crisis of 2008, the change is going to be more like +3%, +4%, or even more from one day to the next. So it will be say +4%, -4%, +4%, -4%, and then it goes back down to +1%, -1%. And so this idea that the amplitude of the steps is something which is not constant, but instead something which is which is dynamic, is something which is sort of obvious when you look at the prices. Obviously, it triggers a question: how would you prove that it's more relevant to model prices in this way compared to the standard random walk or standard random motion? If you want to play a bit, you can. So if I go back to these equations, maybe I don't have much time to explain what is the behavior of this new T process. So essentially, just in one word, it's going to be what we call a mean reverting process. So meaning that it's going to be centered on 0. If it deviates from 0 up or down, it's going to come back to 0. So because my coefficient A here is between 0 and 1, if you forget about this random contribution, so this would be just a geometric equation, and so it would be just a geometric sequence, and so it would come back to 0, just like with a geometric decay starting from one given value. And so this process it's something which is going to, on average, decay to 0, but at some times, because of this random contribution, it's going to spike away and move away from 0. So it moves away from 0 and goes back away. And so this is probably, from the intuition again, it's something which sounds a bit like what happens, say, in the 2008 crisis or the COVID crisis, for instance. So first of all, it spikes and then it goes back to 0. And then you compute the volatility as the exponential of this value, and then you inject this volatility in the random walk. And so the amplitude of the steps are going to be small, small, and then super large for a while, and then back to small. Final question, maybe. So this is a generalization of the random walk. So and so the question is, what do you think that the Cox-Ross-Rubinstein model, which I presented before, do you think that this model would be compatible with this stochastic volatility modeling? So that's a complicated question, which I leave open. And I think I'm done. Are there any questions?
Thank you very much, Jacques-Olivier, for this very nice lecture. So let me remind everyone that you can type in your questions and we will read them to Jacques-Olivier. Some of you have already done so during the talk, so I'll start with those. And if you come up with questions right now, you've got some time to type them in and we'll ask them. So let's start. Just 1 second, I need to access the questions myself. There we go. So first question from Pranav, could you go back to the slide where you had a graph of Brownian motion, please? Pranav is wondering what the axes were on this graph.
Oh, okay. Okay, so on this graph, the x-axis is time, and what I plot vertically is the value of my random process. So if you go to the random walk here, so here you have a sequence of value x0, x1, x2, x3, etc. So vertically, I plot the value of x, and horizontally is the index of my random process. And so here it's the same, but on this graph, vertically you have the value, but here it's continuous time. So, and this is where it becomes technical, as mentioned in the beginning.
Yes, thank you. And another question, again from Pranav, very precise, on slide 71.
Okay.
So let's wait and see. There we go.
Yep. So
does yeah, probably we need to see. Yeah, exactly. Does S0 have to be less than 1 as well as greater than 0, so that PU is less strictly than 1?
No, it doesn't. No, it's the initial value can be anything. and just to make a sort of a funny story about this. So as you can get from this model, all the prices here must be strictly positive, because I start from something which is positive, U is strictly positive, D is strictly positive, so everything is going to be positive here. And in mathematical finance, people use not Brownian motion, but actually exponential of Brownian motion. And so it's very clear from their modeling that everything must be positive. However, in September 2007, the price of gas became negative, which is extremely disturbing, but that's a fact. And it's a very amusing question about why it became negative. And suddenly it broke all models, because it was not baked in. It was like, what's happening? And yeah, so maybe if I have time, I'll explain why it became negative, but maybe there are other questions.
Yes, maybe I also have maybe a question about that afterwards.
Yeah.
Another question from Abir. In the EM algorithm,
yeah,
are the proportions, are the proportion for each group the only parameters that are updated? And if not, how does their value influence the other values of mean and standard deviation?
Yes, so all these 6 parameters are updated at each step. So at each step, you're going to update the mean, mu0, mu1, sigma 0, sigma 1, and the proportion of each group. And these 2 parameters are going to be computed as the proportion of students of grades, say, whose density 0 is larger than density 1, or density 1 larger than density 0. So once you know mu0, mu1, sigma 0, sigma 1, you get the proportions. And then in my naive example, once you've done your split between of all your grades in 2 groups, you update mu0, mu1, sigma 0, sigma 1. So the algorithm is really a bit tricky. It's something that you need to look at for some time to figure out exactly the flow of computation. But in a sense, the code itself is extremely short. It's like it's 10 lines of code. It's essentially it's just looking like, so if you can see my screen, it's just this bit, just this. So it's
really very short code.
So it's really short. It does a really amusing thing, and and that's what it is. So
okay. Okay, thank you.
Yeah.
Maybe going back to this episode where
the price was negative.
Price of gas went negative. Maybe I have a question about that.
Yeah.
You said it broke all models because this number was modeled by exponential of a grounded motion. So as in particular, it has to be positive, I suppose.
Yeah.
And so are there now models that can account for this negative price after this event?
Well, a bit, but it became so maybe I should explain why it became negative. So
yes.
So it's so someone in the market thought decided to buy a huge quantity of gas during the summer, and the contract was so the agreement was decided during the summer. And it turned out that the meteorological forecast in September were quite mild. So and then suddenly you had one person who had to store a huge amount of gas, but didn't have the storage, and he was forced to take all the gas that was bought, but he could not store it anywhere. So he had to pay someone to take the gas, and this is where the price of the gas became negative. It's that so you have many subtleties in say the context of mathematical finance, but in the presentation I made, I just did not say anything about storage cost, but storing costs something. So it's like and so that happened. Yeah, so that was the case. And on the modeling side, because it was very peculiar, because it was only a one-off at the time, there was not so many changes. But maybe you had in the press more recently that interest rates were negative. Like usually when you borrow money, you pay some interest rate, right? But recently you were paid to borrow money. I don't know if everyone got their head around that statement. You borrow money and you were paid for it. And this is not anymore the case these days, but it was the case, I think, 1 year and a half, 2 years ago. And just in terms of understanding how twisted it can be, that's a very interesting question. Why do you get paid to borrow money?
Yes, because now that I cannot imagine that a situation such as the storage problem for gas prices can happen for money. Yes.
Yeah. And so the key thinking there is assume we are currently in very difficult times, and I have some money, and I want to have the guarantee to get my money back in 5 years' time, because in 5 years' time I'm sure situation is going to be better. I'm going to be ready to pay something for the guarantee of having that back in 5 years' time. And this is a negative interest rate. And this is exactly the kind of situation in economical terms that we went in relatively recently. So that's the origin of negative interest rates.
And is this accounted for in some models, or is it the same problem as for the negative oil price?
Yeah, this is modeled properly.
I see. Okay.
Yeah.
There does not seem to be any more questions. So I guess what remains for me is to say thank you again, Jacques-Olivier, for this very nice and very interesting lecture.
Thank you for the invitation.
It was a pleasure to have you here. And everyone, this session will remain open, and we resume at 1 p.m. Paris time. That's in 36 minutes. See you soon.
See you soon. Bye.
Goodbye.